Thank you. So today is the conference to invite Haeusler, actually, he is traveling Sydney. Okay. So Professor Han Haeusler is ARC ITC Center Director and for the next generation architecture manufacturer. And he leading CI of the CRC grant on 3D printing. So actually we share the same program because we just have a grant from China. He got the I grant. So over the past few years, he actually established the traditional design, which is the first global work. So in the future, we're looking forward to maybe hybrid traditional professional so that's looking forward to this future condition. So he coming from university you and established language. He is an language and he is also a researcher, educator, and designer in computer design. And he co-authored 150 academic publications and raised over 16 million Australian dollars research funding. So that's a good verified research funding. He also the head of research control science and innovation at Haeusler Technology, a platform for AC sector that's actually national at several universities. So as well, give us actual topic. The title is Digital Sustainability Thinking for Next Generation.
Good, thank you very much. Thank you, Philip, for the warm welcome, and thank you to the students for coming on such short notice and preparing a poster. So very quickly, as outlined, I've got a few hats. Over the years, I got quite busy in first doing the bachelor degree in computational design, and now more recently having those research projects and starting a little office, taking Philip as an example, that you could be an academic and still a practitioner at the same time. So we try to use a practice as well. So the three main things that we do, or I do right now, is the ARC Training Center, which is a big research organization with 25 PhD students. You should understand that as a vertical organization where we research wide in 3 different areas I outlined later. And then we've got applied vertical, the CRCP as 3D printing, because even we are called architectural manufacturing, we don't really do actually architectural manufacturing research in the center. We do pre and post production and design in the center, but not fabrication. But the CRCP is now a project where we can trial fabrication, and then the bureau is an architectural computing computational design bureau where we can monitor ourselves, what we do through computational tools, and then test and prepare ideas for the ITTC and the 3D printing project. So what motivates us in doing? Well, there are 6 motivations. Architecture, engineering, construction is responsible for 50% of global emission. 50% of all landfill waste is from us. Now imagine if you demolish a building, it's a huge amount of materials. And we also use 60% of all natural resources. These figures are probably from a German context. I used a book from Werner Sobeck. Thank you, for these figures, but I think they would be very, very equal in Australia, in China, around the world. We really took a great part of the problem that we face at the moment with climate change by being architects. At the same time, most of our projects that we deliver are not on time and over budget, and quite often they're not for the benefit of the community. So we deliver projects that are very bad for the environment, they're too expensive, too late, and quite often projects are not needed. So these are the 6 things that just drive us and that we want to do. We've got very, very little time. We have to meet our net zero targets by 2050. So we've got, an increasingly short amount of time, and we have to design at the same time for a rise in population. So probably over the next 20, 30 years, we've got, 2 billion more people coming on planet Earth. All of them want to have a house. All of them want to have a road. All of them want to have water, electricity, infrastructure, rail systems. So you probably need to switch off one of the cameras there. Yep. Okay, no worries. So we really need to be quick. We need speed. So we have to change what we do very, very quickly. And we have to do it on a global scale, so scalability. It's pointless if just one nation solves their energy and sustainability issues. Any ton of carbon that's emitted into the atmosphere will be within 4 weeks around the globe. So it's just not a single problem from one nation or one city. It's a global problem that we need to change rapidly with speed and scalability. And that's the reason why we are interested in second-age machine technologies. So technologies such as social media that produce a lot of kind of data, big data, digital information, Internet of Things, sensors, Moore's law of computing, AI, robotics, machine learning, all the things I think we want to apply because they afford scalability and speed. Just think about if you send an email, it takes you maybe 30 seconds, a minute to write that email. And as soon as you send that kind of emails, it's everywhere immediately. So just immediately in Australia. So you've got speed. You also got scalability. It's not any difference for you if you send the email to one person or 1 million people. So technically, I could speak at the moment to the whole globe, and it would be no difference for me if I speak to one person or to 1 million people or 1 billion people. So digital technology really have the scalability and the speed that we need in order to solve the problems, the 6 goals I outlined before. So we framework that under the title of digital sustainability, where we are interested in digital sustainability. So digital sustainability for us is the intersection in which digitalization strengthens sustainability. So there's no longer a need for being only sustainable or only digital. Those two things need to come together for a digital transition and a digital transition. So it's a twin transformation, twin transition we're interested in. So I think there's 3 steps of scaling digital adoption while reducing global emission. We are very much interested in the business of architecture. Quite often when you work in an architecture faculty or you've been researching an architecture or you're an architecture student, you think about architecture for capital A, architecture. Designing nice buildings, designing suitable for people, fabricating architecture. Architecture is also a business. Any firm that you have is a business. Decisions that we made in the firm are business decisions that either drive if you're going to go down the pathway towards sustainability or digitalization. It's a business decision. Your director might say, I don't want to engage with Revit. It's a decision a business can make. So looking to business and the data within business of sharing the data, connecting the data, making sure that these data are transparent is one of the first principles we want to look into. Second thing is a generational kind of thing. I was educated in a world where computers just started playing a role in architecture. I draw by hand. Many of your colleagues or of your professors or in the firm have been educated by hand drawings. We grew up in a world without computers. So if we want to work together, you need to educate people. You need to educate an older generation, but also younger generation, because the skills you have now will be different skills in 5 years. Digital technology forces us to constantly be agile and changing what we do. So we have to train on a larger scale. But we also need to foster collaboration between different departments. It's no longer possible to only stay in architecture. You have to be a translator between design intent, engineering, science, biology, lots of different areas. So we really need to foster collaboration amongst digital and sustainability and different teams within the organizations in order to thrive. So we're looking into 4 areas of high impact digital technologies, like decision-making support technologies, when AI could support you, augment you in your decisions. And we use it every day. Now, I got augmented this morning on the way here by Google Maps to understand, is the taxi driver actually going the right direction, and does we arrive on time? I got augmented by Google Translate of speaking to the guard outside the door where I want to go and what I want to do. So I think the human augmentation of AI is used in so many areas, and it should be used better in architecture as well. Sensing control technologies, we've got a sensor constantly with us that can sense whatever we do. I think there's a huge opportunity for architecture as well. Enabling technologies, architects are not very good in using tools that are existing on the market outside architecture. There are lots and lots of platforms around that enable to operate your business better, to run your business better. And I think we have to include these technologies as well into our architectural thinking. So really using foundation technologies that exist within our current operation to design better. Werner Sobeck, an engineer from Stuttgart, wrote 2 really, really good books, unfortunately only in German. It's a big pity because then only Germans can read it. And in these kind of 3 books, 2 books have been published already, he talked about that we have to start from what is, I think, looking into some sustainable concepts that agree on we only need to build in timber is an illusion. There's not enough timber around on planet Earth to build in timber. So in his second book, he looked into different strategies to reduce carbon emission. One is reduction by reducing the amount of materials, lightweight structures. We reduce the amount of materials. So therefore, we yes, resources. We'll use, therefore, less waste. We emit less carbon. So reduction is definitely one option. Sufficiency looks at the possibility of reduction of absorption, the needs of the users. I think, unfortunately, it is an illusion to think that everyone in the world will have the same standards of living than a Western world would have. Air conditioning, warm houses, there's not enough material around. So I think slowly we need to come to grip that we need to design better with the materials we have already, potentially recycle materials, and reuse things that we have used before already in our design. And substitution, maybe looking into materials that grow. Timber, of course, grows, but so does mycelium. So maybe looking to biomaterials that grow again, that just, there's nearly an endless supply versus a finite supply at sand. Sand for concrete slowly runs out on planet Earth. So to continue building with concrete is not possible because there's not enough sand around on planet Earth. But is there a way to substitute existing materials with new materials is one of the areas we want to do. So our maps of the world. So that's one of our maps of the world. It's rather complicated, that map of the world, but I think it captures a lot of the ways of our thinking. So let me quickly outline these maps or that map, so different things. In the center, really, we've got the 6 areas that I outlined before. It's really the emission, the materials used, the waste to produce that we need to reduce. On the other hand, on the outside, you as an architect being conflicted probably between the need to design more sustainable, but at the same kind of time, you have to deliver your project on budget, on time, for the benefit of the community. So you're conflicted in the sense, yes, I want to build green and I want to use a sustainable material, but the material costs 6 times the amount of money than the other material, and it comes 3 months later than the other material. And it's potentially a different dimension, so I can't develop my design as I want to. So there's a conflict there. It is quite hard for architects to do these kind of things, but that's the reason why we want to research into them. So then we've got within the area, we've got 3 main areas of our future interest, and I want to outline those 3 different areas in detail now. The one is, we started this designing for computational efficiency. So we've done that for a few years now. In 2014, I established a Bachelor of Computational Design. When the Bachelor of Computational Design, we teach students only computational design. They apply their computational design thinking and their knowledge on tools, on architecture, landscape architecture, and so on, but they're not architects. They've been not accredited as an architect, they've been computational designers. In the same kind of way, if you study industrial design, you're not an architect, you study industrial design. So we argue that computational design has now the need of having its own degree because it's simply to afford certain things that other degrees don't do. So around 400 graduates have been educated already. They find quicker employments in firms than architects because they got skills that architects don't have. They can computer program, they can work on a project with an architect and say, here's a Revit model. In my Revit model, I have hundreds of doors, different kind of doors in my model, and I want to have a door scheduling script that assures that every time we're going to change something in the design, the door scheduling is correct. Very mundane exercise, but needed in the firm. You can do it manually, days and days and overnight, or computationally, where the computer constantly responds to the design. So in computational design degree, we aim to bridge together disciplines like architecture, urban design, landscape architecture, industrial design, interaction design, gaming design, or user-centered design on the design side together with engineering science disciplines. I think one important way of thinking about computational design is the following. Everything we see here that is designed is geometry. You know, that coffee cup is geometry. The room is a geometry. The window melon is geometry. Everything is geometry. Geometry is mathematics. If it's mathematics, you can explain it to the computer because the computer understands math. And then you can develop a giant equation that just takes all these different elements together. And the end of the equation, you've got a building or a city or an object. That's just a matter of scale. If your dimension in one of those numbers is a millimeter, it's industrial design. If it's kilometer, it's a city. And you then got the opportunity to feed in the equation physical elements that comes from different disciplines like electronic engineering or civil engineering. You know, it's very, very easy. You all know that, how to bring a structural calculation into a computer program. You just explain the numbers to the computer program and then the design responds to that. Manufacturing engineering, as soon as it's machine readable, it's machine code, you can feed it out. You can take biological information in there, science information, human-machine interaction, mechatronic engineering. So it's not that our students learn all these kind of things, but they've been educated to think through these things. So they've been opened up to think between design on the one hand and engineering science through the other, through a profound understanding of computation and computing, combined with creative problem solving in a postdisciplinary framework using action research methodology. So they really sit between different disciplines and say, well, if we want to work together, I can speak to different disciplines, and through my understanding and computation and computing, I can do so. So that's the framework of teaching. We don't want to educate cat monkeys. We want to educate computational thinkers. So we place theory and thinking in the center of the degree. All our students will learn computational design theory, thinking, and then apply that kind of thinking with a framework of tool sets and a framework of problems around them to apply. So here's the degree. I can quickly, because we talked about it before, at the beginning, we've got a design collaboration studio. We've got some shared studios that we share with other design disciplines that are not computational. We introduce computational design theory 1 in the first year, where we really explain what is computational design thinking, what do we do different than other disciplines did before, what other people have thought similar than us, and how can you build up that? And then it goes into Grasshopper 1 on object design, Grasshopper 2 building design, Grasshopper 3 on structures using structural optimization, on urban design, then systems where you got a lot of data and conflictive multi-objective optimization, and data where we slowly reach out to AI machine learning as well. So these two courses still using Grasshopper, but more as a sketching tool, because Grasshopper is good, it's easy to learn, it's easy to get into, but it's not very robust. So we're slowly going to go here to Java. We use a lot of homepage programming, or we think that the future of computational design as a tool set could be on the web, so therefore Java programming is what we teach students there. In parallel, you've got then design computing 1, Python scripting on design problems, design urban computing, second Python on electronics, so Fidget, Arduino, Raspberry Pi programming, then robotic computing, where students use Python programming to directly operate a robot. Again, a computational design theory 2 package, where you got a second set of theoretical kind of thinking, more advanced. And then we're going to go into the graduation project where we prepare students in the term here is actually the mouse showing, yep. On the grad projects where they work together with industry partners. So all our research for the grad project comes from industry. So the industry partner brings the problem, and then the students in their last year address the problems through a practical project combined with a thesis writing. So out of these kind of combined mixture between we understand what the problem is, we develop a methodology towards the problem, a question to the problem, we do literature review, and then we develop a response to the problem through a physical. Physical could be a computer program, a code, but also could be something physical fabricated. We've got the graduation project. Then the students submit as a thesis, 4,000 to 5,000 words. The better students are then submitted to Cadrea or ETKE conference, and that's what we submitted over the year, I think around 30 papers or so. So if you see papers at ETKE, Cadrea from myself, since 2015, 16 probably, it's mainly by students, bachelor students. Students also got here the electives. They can choose electives as well. And in those kind of electives, they can choose a minor. There's some traditional minors like integrated design, industrial design, and graphic design. But probably more interesting for the colleagues here is the robotic fabrication minor, where students would have 4 courses in robotic fabrication, where they use the operation of collaborative robots and industrial robots in subtractive and additive manufacturing techniques using different materials from plastic to biomaterials and so on. Social robotics is then more on designing robots, robots that will be in our environment. Is it robots that just pick up dishes in a restaurant and bring them back to the kitchen, or is it a vacuum cleaner, or is it a healthcare robot? I think in the future there's a need to design robots as well, and because you need to design them, it shouldn't be an exercise only for mechatronic engineers, but also designers as well. So some of the projects that we've done over the year, a table we designed for an opera, a little pavilion that we designed with artificial muscles. Didn't really work, but it's research, doesn't matter. Some urban design research, some 3D printing with clay students have done over the year, some media architecture, interaction prototypes as well there. So yeah, every year we've got the computational design conference where students present the results of their thesis and talk about that. So the second kind of bubble is sourcing greener materials. It's a very, very new environment for us. We only just started that in 2023 because I've made a decision that, if you want to substitute materials, you have to start thinking about different materials. So we want to replace carbon-intensive materials with low-emission materials and grow materials with the potential looking particularly into Australian materials. We've got very strict biosecurity laws in Australia, so it's very hard to bring, for example, coconut fibers into Australia from the Asia-Pacific region because of the biosecurity law. At the same time, we've got, of course, lots of agriculture waste in Australia. We produce, cattle, grain, wine, beer, all these kind of things. So each of these agricultural manufacturers produce waste. So we want to look into agricultural waste as a building material in the future. And people looking into various, bio, local or low emission construction materials. Here are a few projects around from other areas. Particularly in Europe, you can see a huge trend. That some photos from Copenhagen from last year in September from an exhibition at CETA in Copenhagen. So I think there is an interest in biomaterials, and we slowly start looking as well into biomaterials by generating out of mycelium elements, structurally testing them. So we can feed the results of the structural test into Karamba. So we then got an opportunity to really calculate computationally what the material can do and how you can fabricate with the material. Robotic fabrication is then another area where we've been looking to. So it's again a rather young trajectory. I hesitated for a very long time to look into robots, not because I don't like robots, but other people like Philip or Achim in Stuttgart are by far too advanced, or the colleagues in Zurich, in robotic fabrication as a research topic. But now through the education framework with the students, I think it makes sense to educate them on a bachelor level. And then through time, I would say there's also a trajectory of the training that we can do research, because in order to do good research, you need talented students that have been trained on computation robotics, and then you can go immediately to a next level because you don't have to start by zero. When you bring the students into a master's or PhD level, they already have some knowledge in. But of course, we also got some funding through a government grant on 3D printing, and I'm going to talk about that in a minute. So we do some little kind of projects. We've got commissioned by Izumi for the Bao back to do some robotic drawings that we're going to do. We do some 3D printing with robots. So we're working on that at the moment. These are acoustic panels using recycled plastic. One of the meetings room that we have in our office, performance is rather poor. So we decided to design some acoustic panels. 6 of the 17 panels were fabricated already when I left. So probably by now, I think most of the panels are completed, and we will install them in the room and then test their acoustic performance and potentially publish. How about that? So the second big research project is really the CRC printing for remote environments using local materials. And for that, probably have to explain a little bit about the Australian context. Australia has probably the same size as China, but in the whole of Australia are probably less people than in Shanghai. So we've got 30 million people over the whole size of China. So that means that not the whole country is empty, but there are certain parts of the country that are rather empty, where you have to travel potentially 300, 400, 500 kilometers between village to village. So if you live in one of those villages and you want to have a house because you live there and you want to live in a house as well, the only way to get a house is by getting a house designed and built in the capital cities. So for example, in Perth, Perth is a big city in the west coast of Australia. And you have then cut the house in half and you bring the house 4,000 or 5,000 kilometers up north to install there. So you can imagine the cost of the delivery is enormous. So normally these houses cost 60 to 80% more money. The house that you've got is therefore a rather poor quality house, and quite often it's not made for the local conditions. You know, Perth has a more moderate climate, probably a little bit similar to, let's say, Wuhan from a climate condition. So, and if you live in the north of Australia, you've got a tropical climate, so the climate conditions are very, very similar than, you know, an area that you would have in Hong Kong, for example. So these kind of houses are not adequate. These houses are expensive. And what we want to look into in our research is changing the design for these houses by using local materials. So we bring the factory there, the 3D printer, and using local materials to design in the house. Sorry, one of you needs to mute HC, the microphone again. So one of the main goals we have is developing a software. There's 3 main goals. 2 of them are from the manufacturing side, from the 3D printing company we partner with. But what we want to do is developing a software that allocates human capital and desire into a location-specific 3D printable outcome. So what we want to do is our vision. Imagine a map of the world, a homepage. On that map of the world, you can identify your site. And with 4 clicks, you say, this is my location. With the clicking on that site, you immediately would get all the information related to the site. So GIS information on that homepage, you would understand what is the setback, what is the building height, what are the environmental conditions, are there heritage overlays, you name it, soil condition, all that. So in the company Giraffe Technology that I co-founded, we already got that in place that you could do those. So I can go to any site, I'm going to click where I am, I can download certain layers that are publicly available. And with all these kind of layers, I've got all the understanding from what is the context of the site. So I can design within a context, or the computer understands the context of the site. The second thing, well, it doesn't really exist in architecture yet, but you already used it when you used Airbnb. When you go to Airbnb and you look for a location, well, you can find a site and you can say, my budget is between X and Y, and I need 3 bedrooms, 4 bathrooms, a pool, a sauna, a TV. You specify what you want. So you want to use the same kind of principles for house design as well. You can go when you've got the site, you can tell me what is your budget, how much can you afford to build a house, and what do you want to have? So it's similar to a brief when you got an architectural conversation with a client at the beginning. You say, what do you want to have? Well, I want a house with 2 bathrooms, 1 bedroom, a garage, a living room, a kitchen, and I've got $1 million to spend. That's my budget. So we can bring that information as well to the computer. It's numbers, so it's easy to compute. The step 3 is then using a template for a house. So we want to go away from the idea that you can design any house that you want to. We want to be more restricted in the same kind of way you're restricted when you buy a car. If you go to a Porsche dealer, you will only get a Porsche, and you can choose between different Porsche cars. If you're going to go to a Volkswagen dealer, sorry, German, only now German car brands, you can choose the range of the car you would have. But within the range of the car, you still got a lot of specifications. You can have different performance of the car. You can have different style of the car, the colors, the finishing, and so on. And whatever you choose will be a different look and feel of the car. So imagine we're going to do the same thing for housing. You say there's 4 or 5 different style of houses. There could be the villa style. There could be the industrial chic style. There could be the alpine lodge style. These are styles that you can explain to the computer as well. If you'd ask a computer with DALL-E, design me a house in a Norwegian wood timber style, well, the computer would understand what it is. It's seen a lot of kind of photos, so you can use that as well. So we want to generate styles. And then with these 3 informations, we start developing a software that will take all these elements into a big computer program. And the computer program will then spit out a machine code for the machine, for the 3D printer to 3D print, Revit BIM information in order to engage other trades or looking into prefabrication, DA, design approval for the government to approve the design. A set of 2D drawings can be generated easily, and visualization for the client, that the client could say, all right, okay, so I can see what the design is. And before I purchase the design, I want to look through the design. So imagine you've got a gaming environment where you can walk around there and you say, well, I don't like the green floor, I want to have a blue floor. And you've been able to change that. By changing one material to the other, you immediately would have information about how much the material would cost. So the price would go up and down, the delivery time of the material. So you would understand the time of the project. So all these informations could be computed. We are also interested in 3D printing for another element when it comes to design for manufacturing, assembly, or modern methods of construction. Normally, when you assemble something offsite and you bring it to site, there's always a problem between different trades that things don't really fit with each other. There are tolerances. Construction normally is not a very precise trade. So you've got tolerances, and we bring 2 parts together and the tolerances don't really match because one thing is 3 centimeters bigger than the other. You've got a clash there. I think 3D printing has the advantage for 2 areas. One, you can make performative 3D printing. Performative means that you can replace a lot of materials that you normally would use to build something with one material. So let's imagine you would build a normal wall. In a normal kind of wall, you would have plasterboard on the inside. You've got some concrete, you've got some insulation material, you've got a cladding material on the outside, 4 different materials. 4 different kind of carbon emissions, 4 different times waste. With 3D printing, you could do another way. You can say, well, if I want to have a wall and that wall needs to perform in a certain way for thermal performance, for example, you can 3D print that performance into the wall. You can write a computer program that says, well, there's certain cavities within the wall, and these cavities within the wall would allow a certain U value of that wall, and you could 3D print it. I think a 3D printer can do by far more than just straight lines. 3D printing at the moment is mainly a straight line that defines a wall. I think performative 3D printing could do by far more because you can compute all the performative elements you want to have in there and then 3D print it. The 3D printer does not care what it prints. There might be some constraints of overhangs or others, but other than that, you can create a performative 3D print. The second thing is that 3D printing is flexible. So up to the point where you press print on your 3D printer, you can change anything. It's the same like a 2D printer, like when you write a piece of text, up to the point where you just print out the text or the poster, whatever you're going to do, you can change anything you want to. So imagine now, whatever, on a construction site, you've got some prefabricated elements like a bathroom pot. Happens very, very commonly. You could just understand the measures of the bathroom pot. And only when the bathroom pot is executed and completed, you take then the measurement of the bathroom pot to 3D print around the bathroom pot. Or even better, imagine you've got a window. There's a window with a certain dimension. That kind of window, for some kind of reason, has now a supply chain issue, so it doesn't really come on time to the site. In your computational program, you can say, well, if I can't get the window now, I can change the design of the window to another window type. But the window looks different dimension in this dimension, but also the profile of the window might be different. So if you would do it in a conventional way, you have to redesign your whole connection between wall and window to accommodate for that change. The 3D printer in a parametric model could respond to that. So if you tell the 3D print that you want to change the dimension of the window from 10 by 10 centimeters to 12 by 12 centimeters, that's an information flow from your computer program to the 3D printer, and the 3D printer could execute it. So you've got a lot of flexibility till the very last moment, the very last minute in your design to change what you want to do. Because the 3D print will only be fixed when you 3D print, and that's happening on the site, potentially, at the time when other materials are already on the way. If you deliver a bathroom pot from anywhere, it probably takes 7-8 hours from a construction site or from a factory site to be on the truck, delivered to your site. In those kind of 7-8 hours, you probably have printed the first floor already. So it's at the time when all the other materials will come out of the factory, you can decide what a 3D printer will look like and adjust to the other materials. So that flexibility is very, very interesting. So we've got, and I can quickly go over that, resources for that. The main thing we're going to do now is to look into the workflow. The hard thing really is for us now to understand that architecture is a job. A job has lots of little kind of tasks. And if you understand these little tasks, you can compute them. Maybe not all of them, but some of them, or most of them. And what we're going to do at the moment, we've designed a house completely conventionally, but we tracked every single step of the design of the house through 2 software packages that do process mining and task mining. So it's effectively a software that sits in the computer and tracks every click you're going to do on your computer, and then uses AI to inspect and analyze what you've done. So the computer software is able to understand, you've done something here, you opened Excel, for example, manually, you selected some numbers, you copied these kind of numbers, you opened that Revit and paste these numbers in there. So the computer could understand, okay, there's an opportunity between a certain number set in Excel and a certain action in Revit that could be automated. So we can identify these little kind of tasks and then compute them in a computer program, assemble them, and do something similar than robot soccer. In robot soccer or any autonomous system, you've got an AI, a task planning AI, that enables the robot to execute tasks depending on the situation. So imagine that the robot is now playing soccer. It looks around, looks for the ball, understands where the ball is, and knows what kind of things to execute. It constantly changes. The situation constantly changes. So task planning takes little computer programs and reassemble them again to something new. So the more ball might be different, the player might be in a different kind of location, but it's still able to autonomously execute what it wants to do based on a task planning AI. So we want to do the same thing for architecture, where we say, well, the situation could be different, but we've got a lot of little individual tasks that have been computed, and the machine assembles these kind of tasks depending on the site, depending on the spatial arrangement, depending on the budget. So these are situations that change, but we don't really have to write one giant script. We have little scripts that have been assembled through the AI. So we're going to do that now through a first iteration with a house, the house design. We looked into what do architects do all day through the process mining, task mining kind of tool. We test certain architectural prints in terms of how we can design them. What is the precision of the 3D printer? Do we really have a millimeter precision or a centimeter precision to calculate these precisions into the script? Does it change if the weather is cold, if the weather is hot, if there's wind in there, and so on? And then looking into how we collaborate and communicate as well. I'm very interested in NVIDIA's Omniverse as a platform of working together because it enables us to bring all different tools together and link to Isaac Sim, a robotic simulation software as well, where we potentially on the long run can simulate what we design and what we build before we build it. If you look into NVIDIA and BMW, or as an example, if you build a car manufacturing plant, you want to make sure that you can fabricate your cars to the maximum. You want to produce every few seconds, every minute a car. I think Tesla is producing every 38 seconds a new car. So in order to do that, you need to simulate everything within your plant as well. So where's the robot? Where's the human? What material comes in there? What kind of process have to be made? How does the factory, the design of the factory responds to that as well? Could that be optimized? So I imagine in our research a future where before you build something and you do something and you potentially got cost overruns in the millions of dollars, give me the millions of dollars and I'm going to simulate the design to the nth degree. To simulate when is the truck coming, where's the builder standing, how does the material come out there, how does a human as a simulation assemble all the stuff. Theoretically, it's possible. They've done that on other trades, on other manufacturing trades like car manufacturing and so on. Why not in architecture? If you can simulate all these kind of things and you can simulate all the risks in there, you probably get a far better understanding of what could go wrong later on site in your design versus doing what we do at the moment is just hoping for the best. Let's build something and we've never done it before. And we're going to spend billions of dollars on that and building something we've never done before. Not very clever. So I think the simulation part is very, very important. So yeah, we've got then different kind of inputs, different kind of tasks that we're going to bring together through a machine model material making nexus. And help through that kind of nexus that we just generate different outputs where 3D printing is one of the outputs. So the first house design that we've done, it's a DA approval. The documentation has been done already. It's really a pseudocode for us where we tried and tested what can be done or how would you do design that we can later explain it to a computer programmer. So that's a quick, like a rapid shot from the design. That's the design. The design is not very important for us. I personally don't really care about the design. The client gave us the design. The client is the 3D printing company that sponsored us. So of course they want to maximize, what 3D printing could be done. They also want to have a showroom potentially for the Middle East. So therefore a lot of bedrooms in there. They potentially see a future as well for the house for mining communities in Australia where workers on the mines who normally works for 2 weeks on the mine and then fly out again for 2 weeks. could live in there and having their own bedroom, bathroom configuration. So therefore, those many bedrooms and bathrooms. Ceiling plan, roof plan, sections to the building. So I think we're going to finish the design by mid-year. We trial as well some opening perforation as well with the 3D print. I think that's more the interesting part of these arches. The main research for us is then really in the detailing of the design. So is it possible that through a computer program, when you change that profile here to another profile, can the 3D print respond to that? Could there be a database of different windows? And the windows are described in their dimensions and their profile dimensions. If I'm going to go through my list and change them, this detail needs to change all the time. Can there be a performative kind of element in there that Karen Dörfler, for example, already is looking to the 3D printing research on that you got a U value equal to a passive house standard, and it's all done through the 3D print, not through insulation. Or here in the ceiling, can you 3D print a ceiling element where within the ceiling you got certain kind of cavities where all the electronics, all the services go in there, where potentially cooling elements could be in here to have a cooling ceiling, where potentially perforations could be in here for air conditioning. So you don't need an air conditioning duct anymore, like the ones you see here. So everything you're going to see above there is all in the ceiling integrated. Again, that you can later take it apart and recycle again the concrete and recycle the other parts as well. So the last project I'm going to talk about is then the external ring. It's really the research, the horizontal research I outlined before through the ARC Center for Next Gen Architecture Manufacturing. We really look into the challenges of running an architecture business and slowly want to come to the center to become more sustainable, become digital sustainable in your design, but you're getting conflicted by various stakeholders, you know, the government, community, finance, ownership, operators, manufacturing. All these stakeholders influence your design and influence the operation of your project. So we have three main research projects in there. The main three research projects are threefold. Architects are not producing any architecture. Architects producing information for builders and construction companies to execute designs so they can build architecture. So what we produce day in, day out is data. All the data we've produced in the past being your analog data through a plan, section, elevation drawing, potentially sheets of paper. But all the data we produce at the moment are digital data. And we do it over and over again. The first action any one of you is doing when they've got a new design in a semester is go to your computer, set up a folder, and in that kind of folder, you name what the project is, and all the data live in that folder. All the data have a sequence. They're historically ordered. So the computer would understand what you've done when you understand it for what kind of project. So you got a biography of a project that has anything in there: photos, videos, 3D models, 2D plans, Excel calculation, Word sheets, email exchange, you name it. You know, there's a digital footprint of your project. So through a machine, you would be able to ask questions to that data. Through a large language model, through other kind of forms, you would be really able to understand what have happened in that project. And I think that's very, very important and interesting, because at the moment, the only way to communicate and transport information on projects is through human experience. I've designed something and I've done it over and over again, so I've learned something. So if I want to share my knowledge, I can talk to you and say, you should do this and that. You should respect these elements. You should consider the following. Problem, of course, is in projects, I can't be everywhere. I don't really understand all parts of the projects because I only have, one person, one body that could be at one location at one time. A computer could be everywhere at all times. An office with 100 people working on one project, the computer would have all the data for them all the time. The other problem is, when I've been a senior person in an office and need to supervise you, I only can spend one time with you at the same time. So I only can talk to you. I can't talk to all of you. So the knowledge I'm going to be able to share with you is limited to one person at one time. A computer, of course, can again share the knowledge to everybody at the same time on all projects. So if there would have been an AI around that would have been able to understand things and say, hey, it looks like you're drawing something like that and that. Keep in mind that regulation 1345667 have changed recently, so you should change the angle of the floor, for example, from 1 degree to 1.5 degree. So a computer could do these kind of things. So it could be a mentor and augment our actions through the knowledge the computer has. So this is this analytics part. We really want to extract our information to then two things we want to, in synthesis, inform design better through machine learning, so it's an augmented machine. We don't want to let the machine design things. You know, we're all architects. The only joy we really have in our life is designing things. Unfortunately, we would do them very, very little. So if you work in a project in an office, you spend maybe 1% on design. The rest of the thing you spend on documentation, on detailing, on communication. I think AI should be on that part. Let us do the design and the machine all the other part. Because I think in order to design something, you need to understand a few things the machine is not able to understand. Empathy. I can talk to any of you and you can talk about what you want to have in your design, and I can read your emotions as a human because I'm trained to understand humans. So you could talk whatever, and I could understand in a conversation with a couple, and they talk about the wardrobe space, that potentially the wife needs a lot of wardrobe space, the husband doesn't want it. Something like that. These kind of human little details is impossible for a machine to understand. We can understand it, so we can design something for a human understanding. Ethics. I don't think a machine will ever be able to understand ethics. We could debate and argue what ethics and aesthetics are forever, because it's very hard for ourselves to describe what is ethics, what is aesthetics. So how can we explain it to a machine? So I think whether the machine should be able in synthesis to help humans to design better with the knowledge that the machine has. The third part is management. Management and business of architecture is my latest interest because the reason I'm an academic is because I've worked in an architecture firm for an enormous amount of time per week, 100 hours per week minimum, because the director of the firm was not able to run his business proper. You know, delays, decisions, employing people, hiring wrong people, not assembling proper teams for proper projects. These are all business decisions. So I think there's also a lot of intelligence within the existing data on business. So business is the third element. So these are our partners at the moment. One partner, university partner, is missing. The Adelaide University will join us. We probably have other industry partners joining us as well. We've been in conversation with 4 or 5 other firms as well to join us, international firms, because we want to bring the international perspective in there as well. We also got peak bodies, the registration boards, the Architecture Institute, the accreditation board bodies, and international academic partners. And hopefully we've got Tongchi as a partner as well in the near future, because I think what we do aligns very well with each other. That's the structure, really. As I said, we've got here still 21 PhD students have grown now to 25 PhD students, 3 postdoc fellows that will work on that, on the research. So in order to assemble the PhD questions, we interviewed industry partners, academics, 50, 60 hours long to define these kind of themes. And defining then those PhD topics. So the PhD topics are given already. What we want to do is we want to make sure that those topics align with each other. Each PhD student is doing his own topic or her own topic. But I want to make sure that a topic 1 and a topic 7 aligns with each other, because we want to make sure that with the 25 PhD students, which transform the industry instead of just having little topics that don't really align with each other. Synthesis, again, what we're looking really, as I said before, in what we can do with the data when we've got the data, and again, having some topics in there as well. Again, there are not many kind of topics on manufacturing. The reason why we call it architecture manufacturing is purely political. The Australian government is not interested in architecture. The Australian government is interested in manufacturing. And the manufacturing industry is arguing that the only way to increase productivity and efficiency in manufacturing is by pre and post design. So in pre-design, pre-manufacturing and post-manufacturing is really looking into design. That's what we do. In R&D, do we do as well? Logistics, not so much, but as well. Post-manufacturing is then sales, service, and distribution. Not so much as well, but from a political argument, we argued what we do is architecture manufacturing. And the way to improve architecture manufacturing is looking to design. I think improvements in architecture construction could be really done on the design side, not on the manufacturing side, on the construction side. When you try to improve construction, I think then it's already too late. Decisions have been already made in design. So concentrating on construction probably is not the right kind of way. So therefore, we want to concentrate on the data, the pre-design, and the management. So again, in management, we really want to inspect what is the firm of the 21st century in architecture. I'm very, very certain firms will disappear quite quickly. If you think about what is happening in an architecture firm when the majority of your work in the firm is done something that an AI could do, then firms will shrink quite dramatically because an AI could do it better. So what is the business of architecture in the 21st century? I don't know. What is the education of architecture in the 21st century? A very important question. If you're going to teach you documentation in an architecture university, there's evidence around that in 3 to 5 years, documentation could be done by a machine. You just train a computer on all your existing Revit files. Then you've got through neurological AI, an understanding they can hallucinate and imagine what a design would look like, and the documentation would look like. Through symbolic AI with mathematical optimization, you'd be able to include regulations and standards to the documentation as well, that a computer would understand if I draw a certain room, the room meets the requirements of the particular site towards minimum size of a bedroom, a bathroom, or so on. So I think there is a very, very high likelihood that documentation will disappear. So if you teach documentation to students now, what will you teach them for? They will never be able to use that when they graduate in 5-6 years. So these are kind of the challenge that we look into and we want to inspect. So that's our homepage at the moment. It's a bit underwhelming because we just established ourselves, but over the next few years, we will have that. If you've been interested in what we do, join us or follow us on LinkedIn on Arch Menu. We constantly post information on the site as well. So where are we now? Well, we've been very, very at the beginning of the project. We've got, I think, a good understanding of computational, so the teaching and computational design over the years. We signed the agreement with all partners for the last few months, 1.5 years. I've been mainly a lawyer, a finance person, an HR manager, because that's all I've done, really. I've done no research, just managing that kind of contract. But we recruited 21 out of the 25 PhD students. There are still some PhD positions left. We've got a call for postdoc fellows. So if you got any PhD students that are looking for postdoc position, we're happy to send our students, send your students as well. And we commenced the research project in February 2024. So just a month ago, we started. The 3D printing project, again, the partner agreements have been signed. We started with the house design, the DA and the documentation is finished. We started a postdoc fellow in March 2024. And with the bureau, we've got 4 little projects. We designed bioshelters and artificial sea reef for the New Sydney fish market, again, where we used computational tools, marine biological information to generate a design, and then fabricated it through 3D printing plastic molds, where we pour concrete in there and we use the plastic again. The pink room is a mycelium research project where we want to heat press mycelium sheets and then fabricate them as a small meeting room installation, so we can test on a long run how the material performs. Acoustic panels you've seen before, and these 3D printing houses is underway as well. So thank you very much for your time. I hope it was not too much and too intense, but thank you for your attention.
Yeah, I think, we have any questions. I think, I very much appreciate the vision and
Thank you.
we're sharing the same common fund, especially education also, all the way to question and social organization, how the future architecture and factory engage into the social process. Spend a lot of energy and may establish the bachelor degree program also successfully of this grant, and which students will be future PhD student will start first to make research on the future manufacture in Australia. We mentioned the background in Australia, the low population density compared to China. It's a huge country, actually very low population density. Focus, especially on the housing project, it's like the stories, and especially over prefabricated based on the logistic system. I think it's a very good vision to play the leader of thinking. I think it's one of the things I appreciate. Compared to my team, actually, over the past 20 years, China is booming in construction part. We are doing a lot of robotic buildings because it's super difficult. Because if you want to change something, you want to make something new, especially industrial over there, it goes super fast, and all the countries are sharing the same regulations, the same flow, and especially what we should do is to try to change from education all the way to process. I think that you can imagine probably we are super good at engaging into the real practice. We actually started almost 10 years ago, and I know already starting more than 30 projects, which is based on the observation that will be the projects. Especially more than 20 projects, we think have some passion to your vision of the design for education. I think the first passion is about the in-situ and offsite representation. I think especially the computer painting we test the project that it will be super expensive if you want to transform refabricate infrastructure by all the basic site. We find is we met a lot of difficulty because the components will be broken on the way, and also precision to paint it in a certain way. Size of the components, it's a straight side is okay, but it's double curvature wall. It's really difficult to show the geometry. We painted inside for the design and also moving all its components to a certain side. It is not super precision how to modify, how to put them together. So, and also it will be broken because the gesture of put it is upside down. If you're moving it, it's horizontal, just the rotating for 90 degrees, it will be broken because the structure is changed, the structure system, these components change. And the plane is hanging and moving the way, it's always be some percentage broken. Touching some hard things with broken. Great kind of thing. So my team and when we practice the robotic 3D computer printing, our suggestion based on the videos we test This is just a concrete finish, but all the way to the city. And the difficulty coming how to integrate installation, waterproof, if you want to put painting in situ buildings site. I think some other questions come because installation always a problem, and also joints.
Yeah.
Putting windows and wall, and also ceilings, things, and the architecture normally is not one layer. You can super big roof, but still the wall should be good.
Yeah.
So it should be multiple layers. So sometimes you want to put outside to be compliant to be some kind of decoration, but still have the layers to be concrete, include some insulation foam and between, but still we have some either outside, inner side, in between, two layers. So I think the building technology also extremely important to engage into the design process. So biggest challenge last week I talked to my team. The 3D printing is not just machine and parts. Most difficult is design.
Yeah.
Design the 3D building is most difficult.
Mhm.
That building is totally different.
Yeah.
The first challenge. Secondly, I also shared some background with Philip Doc. We invite him to this workshop every year. He's talking about it's not 100% of the complete. He designed super high efficient structure floors, save materials, but that floor is not true. They just make all it. Pieces or system. We have any. So the formation process is based on some structural performance foundation, but actually that is not really. So it's also, I think, we should be thinking on if it's partly in situ, partly prefabricated. What's the percentage of reproduction? Maybe the manufacturers should improve more than. So, and also how to redesign and optimize their industry. Some companies, for example, just looking for it can be super big because this city serving 100, 200 houses, and they can just make walls. And some just make windows, and some just easy to make walls. For example, is there any design in this kind of industry goes this kind of technology? Maybe it's not everything manufactured expanding to bigger vision. Maybe something like the Windows new tradition, like hey, it's using the process, it's layers, and it's with brands, material. So that's the tradition things.
Yeah.
Should be.
Yeah.
I mean, but our experience over the past 10 years is not a 100% revolution, but it's like a smart construction percentage. Sometimes it's 70%, sometimes it's 30%. Depends on the structure system, depends on the budget, also depends on design facade, it's kind of static performance.
Yeah. I think there are a few things that I agree with you. There is on one, whenever you got a new material and a new fabrication techniques, you probably need to rethink about your detailing in architecture, like that have happened when steel came into the 1900s into design. You suddenly have to design steel detailing in a steel architecture. Same for concrete, same for other kind of materials that just happened over time. So I think what we are partially interested in and concerned about is just how does 3D printing architecture look like? what you see a lot at the moment is just here's a normal kind of house and normal kind of details from other materials, and you do it in 3D printing. That's probably the wrong way. So probably over time, there will be a 3D printing architecture style involving, and more importantly than the details, to accommodate water problems and so on. I think one element is as well, design is of course one part. The other part is the construction worker. So Mark Burry has now at Swinburne University the okay from the Vice Chancellor to look into a very unique area. So Swinburne University is a university, but also a tertiary education college. So they educate tradespeople. So he wants to bring a team together where architecture education and trade education on 3D printing and other digital elements come together. So the tradespeople get trained on 3D printer to understand whatever what you have to do with 3D printer on construction site. The architects get understand when you design for 3D printing, what does the trade and the machine would have in the material. And I think that's hopefully a necessary step to address some of the problems that you've said. For us, housing, Luton is the 3D printing company. They've sponsored us, so their focus is on housing because the scale of the machine is on housing. And the market they can see themselves mainly is in housing design, but of course it could be extended to other areas as well, to potentially high rise or having the machine then more in situ. I think it's mainly in situ fabrication, not off situ fabrication that we look into, because it's their business model, so therefore we follow them.
This is super important for education, so I quite appreciate your strategy. The bachelor computational design. It's not easy. I just try to establish more than 10 years, but it's super difficult. That's most of the professors, they still design conventional buildings, but as you mentioned, it's a different, if you want to construct construction.
Yeah.
So it's a new paradigm.
Yeah.
That's something we should define industry. So the formation process. It's lucky because over the past 2 years, 3 years, AI is including. We also design our every generation we have a platform, which is parallel to data journey. And based on skill efficiency, we provide more detailed things to training some narrow codes, which should help, especially the style of 3D printing of heating structure. That is the form. Should have some special items. We name it some physical tectonics because this from the generation process all of it. So I think if you want to change from education, different generation. From the understanding form and the process of communicating with the machine, not only the ChatGPT, but also all the way goes to robotics. And redesign the process. And stakeholders could be, agency could be human being, could be a machine. That could be a company. That could be a small, very small team. We all just buy robotics. The future industry.
Yeah, I think it's really needed to have a very holistic understanding that, there's a 3D model that just defines what we want to have. And that probably needs to be changed and altered. And there's the material. Different materials have different kind of properties. The machine, if you use 3D printing or additive subtractive manufacturing, then with the machine, there's always a human component in there where somebody needs to work with the machine together or operates the machine. So I think up to this point, people always had the opportunity to look into isolation, looking to 3D printing only as a one element, or only looking into the 3D model as one thing. I think the opportunity we have through these large centers is to say, well, because we've got the capacity, we could look more holistically into all aspects of the challenge and work on that.
Now it's a teaching.
there are a lot of stuff and from we can.
Mhm.
I think it's really important to have for complication from theory to technique. But no, I'm just curious about I know your project is aiming to for different kinds of architecture or that's architecture. Within the 4 years, I can feel students can learn a lot of computational thinking and technique. But what about the object they are designing for? How they can understand building or city in that sense?
Yeah. Now you're right, of course, like whatever in a 3-year bachelor program, when you study architecture, you're being good in architecture, but you're not good in landscape architecture. And if you study interior architecture, you're good in interior architecture, but you're not in architecture. And the same kind of thing for, of course, with our students, they're good in computation. They're not really good in architecture, landscape architecture, interior architecture. But you have to acknowledge that you don't do architecture or landscape architecture or interior architecture in isolation, you do it as a team. So we see our student as part of a team where there is an architect and engineer want to work together. And because they want to work together and they exchange information through the computer, our students could sit in between them both and say, well, all right, so if this is your design and this is your structure and you want to bring both things together, we can assist you and we can work on that. So they're working aside architecture. Some of the students who are being good have, quite often you've got a design sensibility and you could design quite well, and the education just assists you a little bit with understanding. But the majority of the students are just, they're very concrete problems in an architecture firm that could be addressed through automation. And, I always mention the door scheduling. So the new Sydney football stadium had dozens and dozens, hundreds of different kind of doors. Each time that the door, the room changes, you have to have a scheduling system in there. What is in the room, and does this kind of room, the door, meets the requirement, for example, of disability access or door opening inwards and outwards? That's a computational problem to solve. So they're working on these, or on the structure again with the stadium. With Oricon together, they worked on a shared exchange model system that allowed the engineers, the fabricator, and the architects work together to deliver the project on budget, on time, because the pressure was very, very high for the Women of Football Olympics or games to deliver that. That's where they sit in there. They're not architects. They're not doing architecture, but nobody does architecture anymore in isolation. And in order to do good architecture, you have to work in a team together, and we just offer another player in the team. Exactly. What we find now, very, a lot of students, we've got what was called in the past, a 1-year bachelor degree. So if you got an architecture degree or an industrial design degree or landscape architecture degree from any university or our own university, you could come to computation design and you're going to get an advanced standing. And in 1 year, you got a bachelor degree in computation design. And we're just going to mainly give you the beginning courses here. So you've got a good foundational understanding of computation. But then go back to your own discipline and say, I'm an architect, I can do architecture, but I understand now enough Grasshopper and Python to better work with a computation designer together. Because again, when you come from a framework of my pencil draws everything, and I'm a computation designer, it would be very hard to talk to each other in the joint projects. So we slowly want to reach out to other disciplines as well and say, so we teach in landscape architecture as well in the master's degree, computation design. We teach in the bachelor degree of interior architecture, computation design. So one course, Grasshopper. They're not experts, but at least when we come to them and say, hey, here's the Grasshopper script, they know what Grasshopper is. And they change their thinking towards, hey, I can do my design differently through computation. So I'm more interested in the process than the outcome, because we know with Grasshopper, with computation design, the outcome can change just by changing a parameter. So it's more the process that interests us than the outcome.
So, that's, yes, as you use, you have some minor or major. I don't know percentage. But actual architect design is a major and minor in this. No.
No. So 1.5, 2 years ago, the university decided to streamline their degrees. So we are now the Bachelor of Design in Computational Design. In the same kind of way, there's a Bachelor of Engineering in Civil Engineering or in Mechatronic Engineering, where, again, for financial reasons, students have some common courses. So there's this common course, this is a common course, and this is a common course to the other design disciplines. So there's industrial design, computational design, and integrated design. So within the Bachelor of Design, your major is computational design. Architecture is a completely different thing. So it's also a major. You're going to major in architecture and you're going to major in computational design. The minor is then through these electives, where you've got the opportunity to say, instead of just choosing 6 random electives, you group them with 4 courses together. So these are these courses here. So in the robotic minor, you've got emerging digital technology. That's normally the first course where students say, I've never seen a robot before, I've never touched a robot. Here are some Euro 5s, and we're going to teach you how to use the Euro 5s for robotic fabrication. So what they've done there is they're doing the drawing. So toolpath generation for drawing, easy, kind of risk reduced. Then they had a hot wire cutter and cut out of blue foam geometry. They've done some metal forming, which pin and just rolling around in there. That's the first kind of course. The second course, digital making, we run for the first time. And there we use 3D printing. So the students could come up with a design for a furniture piece and 3D print a piece with the KUKA KR7. So they get then trained to the bigger robot. Again, other OHS proceedings in there, that you can operate a robot. The university is quite strict in Australia. When you want to use the machine, you have to be trained. So it's mainly a training kind of program. Then the Digital Design Foundations is a course we run currently, where we look more into biomaterials. So they're going to use biomaterials in there for building something. And then construction robotics is more like a theory course where we want to explain to students, if you want to design with a robot in mind, these are different kind of robot types, like a 3D printer, an off-site robot or on-site robotics fabrication and stuff like this.
So major and
minor, but you also could have a major in architecture and a minor in robotic fabrication or industrial design minor. So the only kind of challenge then would be, well, you would be, as an architect, understanding what robotic fabrication is, and you have operated the robot. So potentially you would bring into your design thinking the robot in there. You're not able to operate and program the robot. For that, you need computation, you need Grasshopper, Python, or so on. That's something they don't really be able to do.
You have major. For example, the major in architect design, also major in.
Not yet, we're working on that. So we are developing at the moment a dual degree between computer science and engineering. So engineering in general. So engineering is then civil engineering, mechatronic engineering, manufacturing engineering, computer engineering, and computation science. Because then you would have students who are highly trained in engineering disciplines and computation design. And we want to do the same thing with architecture students in computation design. Because then you really would get very interesting people together. You get somebody who's trained as an architect and computation design with somebody who's trained as a computation designer and engineer, and bring them together. And then you really got that mixture of people that could transform the industry.
Students need to spend more time.
Yeah, it's 4 years, yeah. And that's the reason the change of the Bachelor of Design have happened, because with the streamlining of all the courses to Bachelor of Design, Bachelor of Engineering, you always got the same framework, so dual degrees are by far easier. So that's what Nicole Gardner as a director is working on at the moment, of having dual degrees of engineering, then dual degrees with architecture, dual degrees with science. And then you really got that, transdisciplinary, not the silo thinking anymore. That's the problem in the 21st century, because you can't think through silos. You got really the agile, transformative degrees is needed.
I think this kind of assembled knowledge available for the future generation.
Yeah,
They don't know what to do in the future. Maybe just assemble based on their interests. And that would be interesting.
Exactly, because when you graduate now, you probably will change your jobs and your career 4 or 5 times over your lifetime. Yeah. We also don't really know what if we would have gone to our parents and tell them when we've been 20, I want to become an mobile phone app designer for Alibaba, they would not know what we talk about. But now it's completely, everybody would say, yes, that's a good career. Is it still a good career in 20 years? We don't know. But I think what we probably could be certain that if you understand digital tools and digital technologies, and you have an understanding what digital is, and you have creative problem solving and design thinking, I would say you've got a very good chance in the future to be employable, maybe in different jobs. So our students start in architecture as an employment. Then after a year or 2, they get better contracts from engineering firms because they pay more. Then in 3, 4 years later, construction companies hire them. And after 5, 6, 7 years, they start working for Google, for Apple, for Boeing. So our senior students all left architecture and work for other firms now where, creative thinking, problem solving, design thinking, computation play a role.
So the last generation, like,
Yeah.
super master.
Yeah.
So we have like master. So it's always a debate. What's the future of? Someone just focus, especially will be the future, still be architect. But to me, I think the future architect also should be thinking on the problem and redesign.
Yeah.
Not just the sketch.
No. Yeah. And I think that's with the research of the business school to train slowly architects in existing firms where they could be. If you've been a Frank Gehry or a Zaha Hadid, you already got a brand name as much as Gucci or Prada as a brand name, that you probably just under your brand name, you can make a profit in the future by just, having that name. If you're not Zaha Hadid or Gehry, and you're a small firm with 5 people in Shanghai or Sydney, your future will look very, very different. I've got I really fear a lot for these small firms, what they will do in the future. And these are the majority of firms. I'm not sure about China, but I assume the majority of architecture firms are also between 3 to 10 people firms. So if we write computer programs over the next 5 to 10 years that just completely do house design through 3D printing with robots, and you go to any of the provinces, you don't need the architects anymore. So what you're going to do then, even with site inspection, there's no need for site inspection. Computers can do site inspection reports and so on. So very, very interesting to think about, education, about the future of the profession, because the profession will not be the same in 15, 20 years. Yeah. It's just unfortunately that we spent the last 10, 15 years talking to our colleagues about that already. And, they still don't really see what is happening in front of them. They happily adopt, all the forms of AI to have recommendation at Netflix, or hiring cars or ordering food, but that it will affect their own profession as well. They don't really see that.
I think it's quite a good relevant to our research from team and PhD student and instructor. Also have some students come. So it's very good notes to what I'm talking and teaching the team. Thanks a lot.
Thank you for the invitation.
Really appreciate it.
Thank you.
Thank you so much.
Thank you.